Hey everyone, welcome to my speech on ZK 101 here at starknetCC. Before I begin, I'd like to thank the entire team and especially Sam for putting together this amazing event. I'd also like to thank Starkware for supporting it. So first of all, a little bit about me. My name is Daniel Lumi. I'm a Web3 consultant and researcher. I specialize in L2, ZK, privacy, and DAOs. And today we'll be talking about why should you care about ZK proofs? What are ZK proofs? How do they actually work? And then applications for ZK. So why this talk? ZK proofs are extremely complicated mathematics. In fact, it's like having a PhD on top of a PhD. And for many years, there was this select group of us geeks that really liked ZK, and no one else really paid attention to them. But with the advent of ZK EVM, ZK has kind of become a meme, and everyone knows about it. ZK this, ZK that, but no one really seems to know how it actually works. And so maybe you start getting into ZK and you ask your friend to explain how it works, and they go into polynomial commitments or Fry-based recursion or quotient checks. They will. Or maybe you start getting excited into it and you do a little bit of research online and you bump into Ariel's speech on Hassan's theorem. I don't recommend watching it. He seems to forget that most people don't have a PhD in math. Or maybe you just follow some shitty YouTuber and they say, you can make money on ZK. Don't sue me, boy, please. So, why should you care about ZK? It's a new field of math. Yay! That's it. Thank you. Have a nice day. I'm just kidding. And you might say to me, I like math, but who studies it for fun? Or you just might say, fuck math. They're really, really cool. Trust me. Hopefully you stay until the end of this speech and you get a better idea of what ZK is and how they can be used. So Vitalik recently on a podcast said, in his opinion, ZK snarks are as important of a technological breakthrough as blockchain are. And I actually disagree with him here. It's a new primitive in math. I think ZK is bigger than blockchain. What? I disagreed with Vitalik. Come at me, buff bro. So thousands of years ago, when we first invented what's considered modern algebra, there were some farmers that thought, great, I can farm carrots a little bit more efficiently. Or great, we can calculate the largest common denominator of a square to figure out the size of a tile on the floor. But today, algebra is used in everything we do, right? We couldn't have the internet, we couldn't have phones, we couldn't have modern manufacturing, architecture, we couldn't go to space. And proofs have actually been around for a long time. But back in the day, to make a proof, you essentially needed this giant book filled with math just to prove that that one proof is true. And around 2016 to 2018, we first came out with a non-interactive generalized proof, right? And what does that mean? That's kind of like comparing a calculator to a computer. Calculator does one thing very, very well, and a computer can run any program on top of it. It's a new field of math. Like, that's really exciting. When were you last around when there was a new field of math? And today we're the farmers. We think, great, we can make Ethereum a little bit faster, or great, we can log into a website without a password. But thousands of years from now, people will be talking about the moment that we invented generalized non-interactive proofs. So what is the actual ZK proof? In the current paradigm, in the normal world, essentially we had to run every single instruction in accounting or in a program to be able to prove that something happened, right? So in the grocery store example, you need to list the fact that a cucumber is 15 cents, ice is a euro 10, and then you add up all of those items and you get to the total of 15.25. In the ZK paradigm, you can just show the fact that the total is 1525, and you don't need to actually run through all of those transactions to prove that. So zero knowledge proof is a new type of cryptography where one party, the prover, can prove to another party, the verifier, that a statement is true without actually providing any additional information besides the fact that the statement is indeed true. So how do ZK proofs actually work? And I'll give you a couple examples of this. And the sort of default example in zero knowledge is where's Waldo? And Where's Waldo is an old French book where there was a game that you were provided these big pictures, and amongst all of the people, you had to find Where's Waldo. So the challenge in a zero knowledge paradigm is how do you prove you know where Waldo is without showing where he actually is? And I'll give you guys actually a moment to try to find Waldo in this picture. He's here. It took me a very long time to actually find him for this example. So how do you actually prove you know where Waldo is to your friend without actually giving them the answer? Well, you can cut out the picture of Waldo, right? And then you send that to the verifier, your friend, and they can check the fact that you actually found where Waldo was. But more than the Where's Waldo example, I really like the Sudoku example. First of all, because it's more accurate to how zero knowledge proofs work in the first place. So the challenge here is, let's say you're playing Sudoku with your friend. Both of you are trying to complete the same exact puzzle. And how do you prove to your friend that you completed the Sudoku game without actually giving them the answer? Because then it'd be no fun for them. So what you can do is you can cut out each row and column of the Sudoku. You put them in a list, and maybe you shuffle these numbers around a bit. And then you flip all of the rows upside down, and that's actually what you send to your friend. And then your friend, the verifier, can just start randomly flipping rows. And they can prove the fact that, yeah, you did Sudoku correctly. There's 1, 2, 3, 4, 5, 6, 7, 8, 9. There's no number twice, and there's no missing number. And they don't actually need to flip every single row to be able to prove that you did it correctly. It becomes probabilistically true. We won't really go into that today, though. Okay, great. That sounds good. But how do you actually create a proof? And this is something my girlfriend asked me while I was making this presentation. And honestly, it's a little bit hard to explain without going deep into mathematics. So the example that I can give to you about this is it might be hard to understand how a computer works with zeros and ones, but essentially at the very bottom level, there's zeros and ones. Those go through these logic gates and or, nor, and all of those logic gates are sitting on a circuit, which is the circuit board. And then you can prove that a program ran correctly on your computer without having to worry that something happened wrong. ZK is uses kind of like virtual circuit boards. At a low level, ZK proving and verification systems also use circuits with logic gates. And it doesn't actually use in zeros and ones, that's to simplify it a bit, but essentially it's the same way that a computer works. And through that, you can show that a proof really did happen correctly. But let's zoom into the proof a bit, right? So here's an example. Let's say you wanted to prove that your passport hasn't expired yet, but you don't want to actually give them, for example, the passport ID number or your date of birth. So essentially, you can just flip over all of the inputs that you don't want to show. And then the public inputs would be, for example, your name, the date of issue, the date of expiry. And you essentially do some calculations on top of that. And all of that together, the calculations, along with the public inputs and private inputs, are something called a witness. And witnesses are very important to how ZK proofs work, but we won't really go into that today. So here's an example of how you actually create a ZK proof and how the verifier checks it. So you take the public inputs and the private inputs, and you send those to the prover. You also do you have this circuit that is a relational circuit where you essentially compare, for example, the passport ID number against a government passport database. And the government passport database can give you a digital signature and show that this is really a real passport. And then you send the ZK proof as well as the relational circuit to the verifier, and the verifier can check the fact that you really do have a passport that has not expired without them having to contact the passport database directly. And if that doesn't really make sense, that's okay, because my hope is for the vast majority of the cases where ZK is used, or at least a lot of them, we can abstract away some of the complexity. And the example of this is before Windows and Mac, we had to make a different operating system for every single computer. Depending on the type of CPU it had, depending on the type of GPU it had, you had to program a completely new operating system on top of it. And then came along Microsoft and they created DOS. And DOS was this generalized operating system that could run on any computer, regardless of its architecture. And my hope is kind of the same for ZK proofs, that with some primitives like ZK EVM or Circum, the vast majority of cases, people won't need to actually understand what's happening underneath. They can just program on top of ZK. So you might have heard of these acronyms, Stark versus Nark. And honestly, all you really need to know about them is snarks are cheaper to push onto something like a layer 1 Ethereum and verify there, but they're not as secure. Starks are more secure, but they're also a little bit more expensive to submit onto Ethereum. Starks are used by Starkware, and snarks are used by essentially every other protocol. And part of that is because snarks are older, so there's a little bit more trust in them, and they've developed some more fancy tricks that you can do with snarks. So here's some applications for ZK and how they'll actually change the future. So the first and most important thing that you really need to understand about ZK is it's verifiable computation, right? So an example of how blockchains currently work is on a blockchain network, every single node on that network needs to re-execute every single transaction. And the reason you need that is blockchains work on a majority trust assumption. So at least 51% of the nodes are saying that, for example, Daniel has this much ETH. And you really need a lot of nodes on this network because otherwise someone can come and just hijack the majority trust. And so let's say you have a network where there's 3,000 nodes, and each of those nodes spends 5 seconds on computing a single block. Essentially, what that means is around the world, there's computers doing 4 hours of re-executing those same transactions. And honestly, that's just wasteful, right? ZK is a new paradigm in computing, and you don't need to have every single computer running the same exact transactions because you can trust the fact that that proof was created correctly. So an example of this is you can have Bitcoin with exactly one node, and then you have exactly the same level of security. And Bitcoin currently has around 16,000 nodes, and every single one of those nodes is re-executing the same transactions over and over again in order to keep it secure, again, because of the majority trust assumption. In ZK, you would just need one node to make a proof, and every other node on the network could just verify that this proof was correct, and no one has to re-execute all of those transactions. And maybe the most known use case of ZK is for scaling Ethereum, for example. And this is currently how blockchains work. So think of each of those blue dots as a new transaction wanting to get included in a single block. And the more transactions you have, the more time it takes for the node to compute, or in this case, all of the nodes to compute that new block. And the challenge is you want as many of those transactions to get included as possible to make the network fast. But the problem is because of this majority trust assumption, we want as small of computers as possible. For example, a MacBook or a phone to be able to actually run the network so it can be hijacked easily. And so every public blockchain right now institutes something called a block limit. In Ethereum, that's around 30 million gas. And that's how much computation or how many transactions can get included in a single block. But this limits the blockchain because then you have around, in Ethereum's case, around 15 to 30 transactions per block. In ZK, this is a little bit different, right? So that light blue line is the prover, the one computer that has to do all the work for that block. And again, with the amount of transactions wanting to get included into a block, it scales near linear or quasi-linearly. But the difference here is if you look at that green line below, that's every single other node, right? So all of a sudden you can just have one bigger computer do a lot more transactions, and then maybe you could have around, instead of 15 to 30, 1,000 or more transactions per block because every other computer can be verified by a MacBook or a phone. And that difference between that darker blue line and that green line is essentially how much ZKL2 can scale Ethereum. And in order for Ethereum to become the backend of the Internet of Value, we need to at least match Visa's level of throughput, and honestly, preferably more. And Visa currently does around 20,000 to 60,000 transactions per second, 20,000 on a normal day, 60,000 on a holiday. So the question is, how do we get a public blockchain like Ethereum to that level? So right now, Ethereum does around 15 to 30 transactions per second, depending on the complexity of the transaction. With ZKL2, we can increase that amount around 10 to 100x. 10 in the beginning, and as we optimize the circuits as well as add parallel proving and some other things, we can get 100x. That means we'd have around 300 to 3,000 transactions per second. And then Ethereum's working on this new data availability layer called dank sharding. The first step of dank sharding is proto dank sharding. And with that, we can get around 10 to 20x scalability. That means it's around 3,000 to 60,000 transactions per second. And then for full dank sharding, we don't really have the specifications. It's set in stone yet, so it's hard to make a guess of how much more that would scale a ZKL to. But it would be more than that 3,000 to 60,000 transactions, maybe a factor of 10 or 16 or more. And at this point, we've already beat Visa's level of transaction throughput. But the important note for this is with just one ZKL2. We can have multiple ZKL2s like Scroll and ZK Sync and Polygon Hermes. We can also have optimistic L2s on top of Ethereum like Optimism or Arbitrum. And then there's this concept in ZK called fractal scaling, right? The same exact way that we can have a ZKL2 on top of Ethereum, we could have a ZKL3 on top of the ZKL2, and then we could do L4, L5, L6, blah, blah, blah. And with this, we get substantially higher throughput than Visa, again, just on one ZKL2. And the important note for this is actually sustainable. Unlike most L1s out there, Solana, this is actually scalable. We can have a larger node because that doesn't actually affect the security of the protocol. And with some things, the tricks like data and transaction compression, parallel proving, and circuit optimization, we can scale this even more. And again, because this is verifiable computing, we don't need the entire state of the blockchain to move the state of the blockchain forwards. We just need the last block and then the new transactions coming in. Another cool application for ZK is interoperability. In these examples, it's interoperability in blockchains, but this might actually apply to Web 2 as well. So currently we have a lot of cross-chain bridges, for example, Solana to Ethereum or Ethereum to Cosmos. And the reality of these cross-chain bridges is they're super insecure and they really suck. And the idea is with ZK, we could create a ZK-like client bridge, for example, ZK IBC from Cosmos. And with this, you could take the state of one blockchain, for example, Cosmos, and submit that onto Ethereum, and then take the state of Ethereum and submit that onto Cosmos. And with this, you'd have minimal trust assumptions in the bridge outside of the consensus of the two chains. And this would allow for fairly safe bridging of assets or cross-chain application calls. It's still less than ideal. You still have issues with reorgs on either chain or bugs in the code, and you have a majority trust assumption on the relayers, or you could have some other issues with the relayers. But this is still a lot better than our current systems of cross-chain bridges. We also have this concept in ZK called hyperbridges, and this applies to that fractal ZK system of L2, L3, L4. And the idea is each of those layers would use exactly the same bridging circuit. So the idea is as long as the L2 bridge is secure, the L4 bridge, L5, whatever, all of those will be secure. They have the exact same security guarantee as the L2. And this is also a lot cleaner than a cross-chain bridge because reorgs are handled a little bit better. There are some user experience benefits of this as well. Essentially, let's say you're on a L4 and you want to bridge it down to L3, then L2, then up to another L3. Instead of having to do that like you do in a normal cross-chain bridge, you can essentially just do a burn and mint mechanic. So you burn the token on the L4 and it just magically appears on the other L3. And we can do this because, again, proofs are verifiable computations. So we can prove that this really happened and they use the same data availability layer. We also have this concept in blockchains called atomic composability. And this is a little bit hard to explain, but the idea is, let's say, for example, you're doing a swap on Uniswap. And Uniswap needs to know the price of Ethereum. Essentially, when you make that one transaction, in that same transaction, Uniswap can call a different contract, a price oracle, and actually get the price of Ethereum and then make you that swap all in the same transaction. With cross-chain or these cross-chain bridges, we essentially lose atomic composability. But with fractal ZK, we gain back a sort of pseudo-atomic composability. And with pseudo-atomic composability, this is still asynchronous environment, so we will need to change some of the way that our applications work. But you gain back this sort of composability, safe composability that you wouldn't have in cross-chain bridges. And an example of this is you could take out a loan on Fractal A, you could send it to Fractal B, you could swap it for arbitrage, send it back to Fractal A, and then pay back the loan. And all of that would happen in one transaction, or it wouldn't happen at all, which is composability. And I do have a full speech on next-gen cross-chain bridges and why old cross-chain bridges still suck. I gotta put that online. Follow me at ZK Lumi. Another very cool application for ZK is using it for identity. And the way that our current world works is every single application you sign up with, any single website you sign up for, Amazon, eBay, Uber, food delivery applications, all of them, you need to provide all of your information, or at least all the relevant information to all of those applications. And besides the sort of basic primitive of I believe data is a civil liberty and I should choose where that goes, this is extremely dangerous because if any one of those services gets hacked, your information's out there. And this is an example of this. So currently, when you sign up for a website and you need to prove you're over 18, you actually send them your age. So for example, the user is 32. And that website or service will store your age. And maybe they sell it. Maybe they use it for targeted advertising. Or maybe they get hacked and then that information's out there. With ZK, you could essentially have a digital version of your driver's license, and you could just send a proof that this user's over 18. And that's a lot less useful for that service for targeted advertising or for selling that data because you could be 18, you could be 32, you could be 75, you could be 150. Or, for example, if you want to use a service and prove that you're not from a sanctioned country, right now you have to send them your passport, a photo of it, or a scan, and show this person is a Finnish citizen, for example. And again, they'll store your citizenship, they could leak it, they could sell it, they could use it for targeting advertising, or someone could hack into the website and they'd have your passport. With ZK proofs and a digital passport, you could just prove the fact that this user is not from a sanctioned country. And again, they would store that in the database, but that's not very helpful information. There's a lot of countries in this world. Or let's say you're going to a Bored Ape party or want to join a private Discord server. And the way you have to do it today is you actually have to show to them that you have Bored Ape 334. And now because they know your NFT, they see your account and they see all of your financial history. With ZK, you could just prove the fact that you have a Bored Ape. And then it's up to you whether you want to disclose to your friends at the party or random people you meet which Bored Ape you actually have. And all of these examples of ZK used for identity lead up to what I consider one of the coolest applications for ZK and identity, which is for KYC, know your customer. And right now, when you sign up with Coinbase or Binance, or you sign up to buy a house, or you sign up for a bank, or even to become a Uber driver, you have to send them all of your sensitive documents, your passport, your tax statements, everything that you could possibly have. And this is extremely dangerous because if any single one of these services gets hacked or leaks your documents, someone might even be able to steal your identity with that. And with ZK, maybe your government or maybe your bank would prove the fact that this is a legal citizen, they did their taxes correctly, and then instead of sending all that information to all those institutions, you can just send them a thumbs up or a proof. So when you sign up for Coinbase or Binance or Chase, or maybe you could even use Tornado Cash legally without them worried about the fact that you're sanctioned. Another cool example of ZK is for using it in privacy. And one important note to have here is the zero knowledge in ZK does not necessarily mean that the proof is private. All it means is that you don't have to re-execute the information, like verifiable computing, right? That being said, it can be used for privacy. So there's this interesting factoid that over 81% of the hacking related breaches use stolen passwords or just easily guessable passwords. And in our current world, again, every service that you sign up for, every website, you have to sign up with an email and a password. And the reality is majority of the people in this world does not use different passwords for every single service. And this is a problem, again, because if any one of them gets hacked, they can log into all of your services. With ZK, we can eliminate this. So this is kind of how you currently sign up for a website. Right now, what you do is you go into the website, in that little box, you type your password. The password is sent in plain text, but encrypted over HTTPS to the server. And at that point, your password's in plain text again. And surprisingly, many websites still store your password in plain text. But even if they store it as a hash, if anyone hacks into that server, they can see those logins happening and they can steal your password this way. With ZK proofs, you could essentially sign up for a website by generating a proof of an email and a password combination. And then when you sign in again, you type in your email and password that creates a proof. And it's impossible for anyone to create this proof without knowing your email and password. And the server still stores that proof, but it doesn't actually store any password. So even if it gets hacked, no one can actually see your email password combination. Or another example of ZK privacy is just a private blockchain, or a L2 mixer like Aztec ZK Money. And the idea of this is essentially it obfuscates the amounts that you send to people, or maybe the source and recipient of funds. And this way, when someone gets your address, they don't see your entire transaction history. And there are some other methods to make a private blockchain, such as fully homomorphic encryption or Intel SGX or multi-party computing, but at the moment, ZK is the best way. And maybe FHE will be in the future, but right now, ZK is the way to go. So here's how a blockchain like Ethereum or Bitcoin, a public blockchain, works is when you make a transaction, you have to send all that transaction information. So for example, where it's coming from, where it's going to, how much you're sending to every single node in the blockchain. And they have to have this information for being able to run that transaction. With a private blockchain, you can essentially just generate a proof on your computer. And parts of that proof would show that this person has enough money to spend, and then it would include those recipients and senders and amounts, and some of those would be encrypted. And then essentially all of the nodes on the blockchain just verify the proof and then roll it up into the protocol. And this way your data is never exposed because they don't need to know where it's going to or how much it is. They just need to see that it's a valid proof. And I am ETH based, so my recommendation, if you have some assets on Ethereum and maybe your address got doxed or you want to create a new wallet to use, for example, at conferences for paying for something, I do recommend trying out Aztec Connect. And I do also have a full speech on privacy in Web3. why should you care, and how to improve privacy protocols to prevent malicious users and hackers. And the last sort of set of examples that I would give for ZK is just understanding our world better. Every time we discover a new field of mathematics, we start to understand our world fundamentally better, right? Maybe we understand how our cells work, or how bodies fight off viruses, or how the shells actually form, the pattern on them, or for things like modern manufacturing, or how physics works so we can actually send something to space. In fact, if we didn't have algebra, chemistry, and a little bit of physics, we couldn't even make a pencil. The rubber on a pencil is an extremely complex chemical mixture, and the lead took hundreds of years to develop in a way that you could actually write with it on a piece of paper, but not tear up the piece of paper. And ZK proofs don't just apply to Web3, right? The same way that any field of mathematics doesn't just apply to one thing, ZK proofs in general apply to computing and other parts of life. And here's some examples of this. So, for example, in this current world that we're in, we don't really trust the source of photos anymore, right? Maybe it was a deep fake, or maybe an AI algorithm created it. With ZK, we can actually prove that a photo was taken at a specific location and a time. And even if it's modified later, like it's made smaller, bigger, there's a black and white filter on it, we can actually prove that this photo was really taken at a location and a time. And then if someone comes in and, for example, photoshops the image of Trump's face onto someone grabbing. Maybe I shouldn't make that example. If it's a fake image, you can no longer create that ZK proof, and we know this photo's not real. Or maybe ZK could help clouds like Google Cloud or Amazon Cloud with proof of storage, or not having to re-execute all the information across all of their thousands of data centers. Or this is something that is actually being worked on, or starting to be worked on, is maybe we can make computers faster with this. Maybe we can make a layer of cache of zero knowledge proof, so that any computation that a CPU or GPU did before, it never needs to do again. Or maybe we can make machine learning more efficient. Or maybe we can understand black holes and how they work. And I actually saw a research paper on this where some properties of black holes might actually be explained by cryptography rather than regular math. And so maybe ZK proofs could actually help us understand how black holes work. Or the last example is honestly a very silly example. It's more of a high thought than anything. And normally I wouldn't even share this kind of an example, but I talked to some quantum physicists about this, and actually maybe there's something to it. So this example is for quantum entanglement. We have this property in quantum physics known as quantum entanglement. And the idea is two atoms can come close to each other, and then they get entangled. And then even if they move apart hundreds of kilometers or millions of kilometers, they essentially share the same exact properties. They move in the same ways, and they change exactly in the same ways in exactly the same moment. And that doesn't really make sense to us, because information shouldn't be able to travel faster than the speed of light. But again, this is kind of a silly example, but that kind of sounded like a proof to me. They come near each other, they create a proof, and then no matter how far away they go, they share the same state. So maybe ZK proofs would actually help us explain how quantum entanglement works. So the point of this whole speech is math is super cool. Just kidding. Whether you like math or not, ZK proofs will affect the world around you, and it's worth paying attention to it. Thanks for caring about ZK, and hopefully you didn't fall asleep or get confused on this, like most cases where I've seen someone trying to explain ZK proofs to someone that's not a mathematician. You can follow me on Twitter at ZKLumi, and thanks again everyone for coming out.